Okay, so I want to thank first the organizers, Peter, Chris, for the kind invitation, also for hosting us for the topical group. I came with Jorge Casanova and Lucas Lamata, two postdocs in my group that take care of these things that I will talk about. It's okay with this, or perhaps a little higher position? You said that it is recorded, right? So I will try to say things with meaning. I plan other things, but so and concerning. Okay, that's fine. So fine. I need to walk a little bit. So when I was discussing by email with Peter concerning the topics of the workshop and the topical group, I received a very nice email from Peter that I like a lot, inviting us to be more risky and to say some speculative things. And in principle, it was meant to be in the topical group, but given that a lot of people leave, so I will just plan to say some not crazy things, but some personal opinions, concepts in quantum simulations, what I consider that are the new perspectives. And as any theorist, of course, we are in charge also to try to be a little advanced of what is possible in the experimentals part of your work. Okay. Of course, you are invited to ask questions. This is also, I think, since Jake Taylor's talk at the beginning, so it's very nice to I mean, it's better not to finish the talk, but to have an opinion about the topics. So, as I said, the title of this workshop is Quantum Applications with Trapped Ions. Given that I left a career in engineering, I have some allergy to the term of applications. I try to do fundamental physics, but of course with applications. So in principle, sure, we can also speak about these things, and I will tell you how I see quantum simulations in trapped ions in terms of applications as communicating vessels between unconnected fields, which I find the most interesting aspect of quantum simulations. Also, as I used to call it in more wide conferences, as our quantum theater in the sense of imitation. No? And I see really quantum simulations not as a very novel field started by some opinions or papers of Richard Feynman, but is the fundamental of theoretical physics and mathematics, the associations, the imitations, and the theory of representation. No? And I never miss either the aesthetic aspects of physics and of making these analogies. And as I write here, it's also a means of stimulating creativity and improve our aesthetic experience. At least that's why I do physics. And of course, we should not miss also the good funding that we get, justifying our efforts when we will one day scale up models in quantum simulations that will be able to retrieve some new knowledge that is impossible for classical computers. Okay, so that was I prepared this a few hours ago just to motivate and that you get the point. This is a photograph of a sunny day in Bilbao in my group. As I said, Jorge and Lucas are around. Most of the things I will say have been developed by them, so I invite you to approach them, and they are ready for discussions. I will also motivate the talks that they will give next week. Most of you will not be there, so I just want to advance some things. These are more or less the topics. Our group tries to develop some particular way of doing research. I mean, I have a hard time putting research lines. We work mostly based on ideas. If we have a nice idea, we look for the knowledge and we try to develop. So for the moment, we are there. So it will grow, probably. This topic of quantum simulation, of course, is framed into the general field of quantum information. And this is just a pedagogical triangle. Of course, you can put more vertices. Quantum communication, for me, is already in the industry. There is very little new physics or fundamentals at this moment. Quantum computing, even though I also work in this topic, I find it impossible, and I don't see any future scope for that. But of course, I criticize this from inside, and I find quantum simulations really in the middle point, where we can still mix fundamental physics with potential applications. It's really the subject that is having the nicest, let's say, flesh for research in this moment, and we are heavily concentrated in this topic. I want to give my own definition of quantum simulation. As you see, I have nothing against beating classical computers, but I think it is a technological goal. I work also on that, but it is not the only one, and this is my definition. I always put this intentional reproduction because I don't consider, for example, monolayer graphene as a simulator of a 2+1 Dirac equation, just because it just appears from first principles. And it is a means of reproducing the quantum dynamics of a physical system onto another one that is typically more controllable. It's a very careful definition. Of course, you trace these ideas back to Richard Feynman, but Feynman didn't invent analogies in mathematics or in physics. He just put the finger on a very interesting topic that when the limits of classical computers will arrive, we will be able to use nature or simulated let's say, experiments to produce calculations for us. Since I was in Athens a few years ago, I realized the association to the theory of theater and on imitation that was developed some centuries before Christ, and I invite you to have a look to this. It's very interesting. So for me, we are just in one of the last steps of this general concept of imitating and developing analogies first for aesthetic reasons, but also for the sake of getting new knowledge by this analogy. Okay? So now I will be more precise. Why these quantum simulations are interesting, in my opinion? The first reason is because we can discover these analogies between unconnected fields, and it yields this bidirectional flood of knowledge. And I just give you one example, that is my personal research associating the quantum Rabi model, which is the dipolar coupling of quantized light and matter, with the Dirac equation. I will mention a few things later. Where I really, at this very moment, there are many things that I understand from light-matter coupling using relativistic arguments. And there are many things that I can understand from the Dirac equation just using concepts of light-matter coupling, as I will tell you later. The second reason why this is interesting is because we can study behaviors that are absent in nature. I'm very uncomfortable here giving you the back to Peter. That's fine. Huh? I think everybody's felt this, but I'm polite a little bit. You can study behaviors that are absent in nature, others that contradict physical laws, but we can also compute inaccessible quantities without full tomography. And I will give you some examples. Of course, this may sound strange to you, but it is very recent research. An example of behaviors that are absent in nature is the Zitterbewegung that was developed. I'm very happy that here is Lucas Lamata and also Tobias Schetz. With them, we developed a nice paper in 2007. In the group of Reiner, they implemented the experiment. And this prediction of the Zitterbewegung, that is a weird prediction that a free relativistic particle performs helicoidal motion, and in the case of the one dimension, it goes forward and backward in absence of potentials, is a prediction of the Dirac equation. Many people say that it is a nil prediction. It has never been observed for relativistic electrons. And some people say that it is just inexistent. However, this physics fundamentally does not contradict anything in quantum mechanics. That's why I put in the category of something that may be absent in nature. Since the very moment where you implement in an experiment a relativistic dynamics performing this Zitterbewegung, in this very moment, the mathematical model associated with this physics exists. No? So this is for me an important thing. How you define the existence of a model is not that nature provides it directly, but also experiments that may produce this physics where the explanations are much nicer. In the case of, I put here some behaviors that contradict the physical laws. I will tell you something about simulating or imitating physical operations. This is a topic that we created a couple of years ago, and we are heavily working in this. And you will see that it's not only for fun and for aesthetical reasons, but you will see that we are able also to present some ideas in which these embedding quantum simulators, that we call them, will be able to give you information that is otherwise impossible. And this is the third example. The third reason, of course, is the ones that gives us our funding. And we will be able very soon, I think, in several experiments, in trapped ions 2, the possibility of extracting information that is impossible for classical computers. And the examples I give here are interacting fermions and bosonic models, and also quantum field theories, which are problems in physics that require really heavy computing. And the last reason is mine, depending on the day. You see, just creative minds are unhappy with reality. See, like any artist, and we are also artists in physics, and when you are unhappy with reality, you create. That's also quantum simulations, a place where you can put at the same time quantum physics or music or theater, if this is what you like. Fine. The technologies are diverse. Of course, this workshop is related to trapped ions, and we have also worked heavily in this topic. Jake Taylor mentioned nicely circuit QED. I will also mention some examples in this topic. Quantum photonics has produced some things, and optical lattice is mostly kind of orthogonal topics. There is a small complex of inferiority, I would say, trapped ion circuit QED with respect to optical lattices, and I will try to compensate saying some things about fermionic and more interesting models. No? It looks like life in trapped ions ends up with some spin models, but I think it is time to convince ourselves that trapped ions can also reach more elaborated models. This is a nice example that I already mentioned to Dave time ago in the 60th birthday of Rainer, and I hope he doesn't disagree now. But you see, the James Cummings model is considered the simplest light matter coupling, as you know, but it comes from many approximations. You need single mode approximation, two-level approximation, rotating wave approximation, dipolar coupling, etc. And I was very happy, of course, the day in which I studied in my PhD, that you can also produce this James Cummings model in trapped ions. This is a figure that I robbed from Rainer. He always accepts, but one day he will charge me. And I saw it also in this workshop. No? And it was very nice when at NIST, Dave and his team was able to build this James Cummings model, again, with more sophistication. It requires two rotating waves, the optical, the vibrational, the lambda regime, and so on. I will not teach you things where you are experts. And it is called the red Seibern excitation in trapped ions, and it produced a very similar dynamics. I consider this as the first quantum simulation in the lab in quantum optics. I would be very happy that you contradict me and you give me another example, but for me this is the first one. Of course, at that time nobody called this quantum simulator, but this is the way I see it now. And I just wanted to point out that at that time, when people just saw the relation replacing quantized electromagnetic field by the quantized motion, nobody said what for, how you beat classical computers, why should I reproduce artificially something that I have it already in cavity QED, for example. You see? I think that at that time people just enjoy the analogies for fun, for knowledge, and I just want to give you an example of how this happens. You start just by trying to make a plain analogy, probably without any further physical consequence. It is very hard to say that by doing this in trapped ions you will learn more about the James Cummings model, right? However, immediately people realize that for mimicking this James Cummings model you need to put a certain frequency of the lasers in those times, or even now. At least I think they use this bichromatic driving with adiabatic elimination, but they just change the frequency of the lasers and produce the anti-James Cummings model, which is just unnatural. You don't find this if you take a two-level atom and quantize electromagnetic field, you don't get an anti-James Cummings, at least in a resonant way. And then this can be built. It is the blue Seibern excitation. And again, just by trying to mimic, you jump and you create a new dynamics with new properties. Then people would say, okay, but what for? I want something that is unnatural. Then came immediately, I don't know if I have I didn't put a comment here, but immediately came people and started to work, and I always give this example, in '95, this PRL of Sirac Soler that was able to produce the first possible implementation of 1 and 2 qubit gates for the sake of a scalable quantum computer that at that time required carrier excitations, but at the same time the shelving allowed by the anti-James Cummings and by the James Cummings. So we start by just developing a plain banal analogy, I would say, and then immediately we create new interactions and immediately we create applications. So that's the way physics works, and that's what I wanted to defend a little bit in this talk. The second example of quantum simulation, just for fun, because it's very timely, is the case of circuit QED. When in this Nature paper of the Yale group in 2004, again, they were able to produce the James Cummings model in circuits, and at that time, fortunately enough, nobody said, what for again? Why I want another James Cummings model with the same properties if I don't gain any physics, any knowledge, any applications? This was a huge mistake done by many quantum opticians. I was one of the first to jump into this topic in 2004 and 2005, and most of the big shots at that time said, you are wasting your time. There is nothing to learn in that setup. It's the same interaction with absolutely nothing new. See, that's more or less the example, and I think they did a huge mistake because, as I said in a conference in Munich last week, and it was very painful for some colleagues, at this very moment in circuit QED one can do quantum optics that is beyond the possibilities of the original quantum optical setups. You see, you can reflect a single photon in a two-level system in a 1D free space. You can reach ultra-strong coupling regime beyond rotating waves that you cannot in quantum optics, and many other examples. But this workshop is not related to that. But I can tell you that it takes the best of microwave cavity QED a la École Normale, let's say, and the best of the optical cavities, if you want it a la Kimball, a la Caltech, or a la Max Planck Institute, the way you want. See? But it's really a playground for doing very interesting physics, and it started just by mimicking a banal James Cummings model. Fine. So now I just wanted to review a little bit how we developed, as I said, in 2007 and later in a Nature paper by Reiner's group in 2010, this physics of the Dirac equation. And again, I want to defend the fact that the main goal of reproducing, I will not give you details because it's old stuff, let's say, a few years, but as I wanted to say, the goal of reproducing the Dirac equation for one relativistic particle into a trapped ion was not to scale it up to beat classical computers, but the main goal was to prove that at theoretical level and at the experimental level, one is able to encode relativistic quantum mechanics in a non-relativistic quantum setup like a single trapped ion. See? At the same time, we learn a lot, and I can give you one example. I mean, probably you will want that I justify all my arguments, but what can you learn, for example, relating a single trapped ion with the Dirac equation? I tell you what I learned, one of the things I learned. I was very impressed that when you have here, for example, where I have this here, have it here. You see, this is the Dirac equation in 1+1 dimension. You have a kinetic term, you have the relativistic mass term here, and this is the language of trapped ions that was just combining carrier interactions with James Cummings, with anti-James Cummings, no, as I said before. And immediately I realized something very funny. When you see the Dirac equation, immediately you see a term sigma x px. If you are familiar with these interactions in quantum optics, you will remember that these kind of couplings produce Schrödinger cuts in a resonant manner. And the Schrödinger cuts, because sigma x, you take the two eigenvectors, eigenvalues, and the px just produce displacements conditional to the internal spin of the ion. And then, of course, when I saw this, I said that's impossible, because it cannot be that the Dirac equation is creating a Schrödinger cut that is growing ad infinitum, because I mean, this cannot be a prediction of relativistic quantum mechanics, something that grows and grows and grows and produces energy. Then I saw that, of course, you have the mass term, and the mass term in 1+1 dimension behaves as a sigma set, which is just a detuning in the two-level system. Then immediately you can make a second-order calculation, and you will see that you go towards the Schrödinger equation, and this Schrödinger cut is bounded, so it cannot grow ad infinitum because of the presence of the mass. So you conclude that a relativistic particle just doesn't produce Schrödinger cut without the coherence because of the presence of the mass. And then that's what happens with the relativistic electron. And I was able to understand how arguments from quantum optics in terms of the tuning and Schrödinger cuts could explain the physics of why a relativistic particle is just not growing in dimensions and so on, and vice versa. There are many things that you can exchange in knowledge, and you can understand and predict better the behavior of both systems. So the physics, you can have a look here. Lucas and Tobias are here, and you can ask them more things. These are, sorry? Yeah.
How would you then implement the Dirac spinor? Because here you don't have...
Good question. As I said, I assume that some of you know, but I'm happy that you ask questions. This was just in 1+1 dimension, but in this paper, thanks to Tobias, we also show the complexity of the 3+1. And as you said, in the Schrödinger equation, we have a scalar wave function. And in the Dirac equation in 3+1, the algebra forces you to use 4 components. 2 of them are associated to the spin, is considered the ab initio prediction of the spin 1/2, and the other 2 are associated with positive and negative kinetic energies of the relativistic stuff. In 1+1 dimensions, the algebra allows you to use only 2, and then we codify it, let's say, in a 2-level ion in a simple way. You see? But in 1+1 dimension, the spin disappears and survives. The 2 internal components are associated to positive and negative energies.
Yeah, but the nice thing is that when you have the negative component, then you have the positron, so that...
That's right. So that is considered historically the prediction. It's questionable, but it is in the books. You see, it's considered the prediction of antimatter and the prediction of spin 1/2 in these models. But as I said, The point here was just to prove that a relativistic quantum dynamics can be encoded in a clean way in a non-relativistic one. That's the main thing. And then you open the Pandora box for whatever you want, just for physics or for creativity or for whatever you want. No? But that's more or less the story. In this experiment that was done in Rainer's group, what I like a lot also is that I was very criticized because, of course, the Zitterbewegung, you have to measure the expectation value of the position of the ion. And I was pretty surprised that at that time, nobody in the trapped ion community had measured the position of the ion in a coherent and controlled manner. I had some ideas that were implemented in this experiment. In fact, it's one of my most rejected papers from absolutely all journals. But at the end, I said, this is what I have. And then I remember Christian Ross, always very honest to opinion. He told me, we had an afternoon, we said, your method is the worst possible. But then when we compared with all the others, I said, okay, we have to use that because there is no other chance. And it worked pretty well. You see, in fact, the resolution, this is the width of the ground state of the ion. See, so you had to resolve really the expectation value of the position in terms of delta, which is the width of the wave packet in the ground state. Of course, the error bars are not wonderful, but it was a clean observation, not of the Zitterbewegung, but of the Zitterbewegung, let's say, physics behavior. No? Many people confused at that time and said, that's not true, the Zitterbewegung does not exist, people wanted to send comments to PRL and to Nature. It's just a mimicking of the physics of the Zitterbewegung. I don't know if you are aware, but the graphene community was constantly looking for that. There are like 20, 30 theoretical papers saying how to observe Zitterbewegung in graphene. Up to now, they have not managed. So it is the only experiment that was able to put in evidence the behavior of the character of the Zitterbewegung until now. Sorry, no, there are in optical lattices some other people. I think, sorry.
Question, what is delta again?
If you take a trapped ion in a linear Paul trap and you put it in the ground state of the motion, see the width of that wave packet is typically 10 nanometers, if I'm not wrong, 5 to 10 nanometers, right? That's more or less. Now, the beautiful thing also is that many people thought that Rainer was able to put the ion at relativistic speeds. Of course not. See, the effective speed of light was 5 centimeters per second, I think. So it was really a mimicking of the physics. But then immediately this method for measuring the position was extended to other things, to other experiments, and you have a bunch of things, and there are plenty now of experiments in photonics, in optical lattices for producing this physics. No? Again, also some people raised their hand and said, why should I reproduce the Dirac equation in a trapped ion if I can calculate it in my laptop? See, this is the typical engineer mentality. That my money just tells me that I have to build classical computers. There is nothing else than that. It's a huge mistake. No? And I want to mention that afterwards with Jorge, who is there, we predicted also that you can observe the Klein paradox. And people have overlooked that this experiment for showing how a relativistic particle tunnels inside a potential and has a propagating solution even though it is below the potential, this is a prediction of the Dirac equation, was done, if I'm not wrong, Rainer, with a Hilbert space of 200 dimensions. You see? So 200 dimensions under total coherent control for being able to prove this banality, if you want, you see? But other people can publish a control knot with a 4 dimensions. You see? This, my nephew can do it without a laptop, see, to make a control knot, 0, 1, it's a banality. But this experiment and this analogy push the limits to make an experiment where really using high dimensionality. So you can tell me which other experiments in trapped ions have controlled coherently a Hilbert space of 200 dimensions. No? That's really pushing even towards applications, if you want. But that's a very nice experiment of the Klein paradox. This was done already in graphene, of course, by the 2 Nobel Prizes too. Novoselov and Guy. Okay? So now, continuing with this spirit of sharing some ideas, some of them more radical than the others. And let me see my time. So I'm fine, 20 minutes. Right? So in Munich last week, I also wanted to push a little bit this. It's not a semantic issue. Be sure that it's relevant. No, there was this discussion, analog or digital, and this is a constant debate. No? Recently, somebody told me, great, we do digital stuff, but if you make the digital simulation, for example, of spin models or of interacting fermions, then tell me how you will be able to reproduce some condensed matter properties like ground states and so on. You need an adiabatic approach. So there is still this debate. Some people prefer analog, other people prefer digital, but each of them has advantages and disadvantages. So that's a very interesting topic. Tell me how you will make an adiabatic process in a spin model, for example, if you are using digital methods, you see. And speaking something bad about the analog, that there is a limit, you see. You choose a setup, for example, trapped ions, you have the fundamental interactions, and then you can do what you can do. You cannot do magic, you see. So the digital is also a solution for the limitations of the interactions. But the other debate that I wanted to start today with you is also this one. Once I was giving in Madrid a talk for the general public, and there was a computer scientist, a classical one, no? that raised the hand and said, how you make the difference in your stuff between emulation and simulation? So I said, okay, wait a second, I go to Wikipedia to study a little bit, and now I have been studying this difference between emulation and simulation. Andres Sorensen last week told me, oh, I will buy your stuff and I will only say emulation, but it's not yet clear to me. When I was starting with these relations between simulation and emulation, I only found, Hartmut Hefner left, or probably he wanted to, I'm sorry. See, I think you wrote, or in Nature or in Science, some review, and I saw in the title emulation. But then I read it, and I think you meant simulation, emulation, just as a similar word. But there is a difference. And I mean, simplifying, when you try to make an emulation, you don't care much about mimicking the internal structure. You only care about the input and that the output is as close as possible to what you want to mimic. While a simulator tries to really build step by step internally all the behavior. Then when I read this definition, I started to say, then what we are doing, for example, in trapped ions or in quantum optics, we're doing simulations or emulations. At the beginning, I went to the radical way. I said, nobody has ever done a simulation in quantum optics. All of what we have done is just emulation. And I invite you to discuss this. You know, at this point, I was checking the paper of Tobias, and I said, no, that's closer to a simulation, in the sense that this quantum magnet in nature physics, you use these two-level ions, and then you really try to encode a spin 1/2 into a two-level system that obeys the algebra of a spin 1/2, you see? But then I said, what about our Dirac equation? And I am almost convinced that we never did a simulation. Rainer, in theory you do whatever, no? But in the experiment, it's really an emulation. Why? First of all, because you are not kicking the ion at relativistic speeds. Second, you are fabricating the structure, and then some people say, yeah, but you fabricate the Dirac equation. Yeah, but it's not in the Schrödinger picture, right? So for calling this a Dirac equation, we have to make several approximations and then even go to a certain interaction picture where this physics will appear. So there are many, many steps, and I have hard time now to say the Dirac equation was a simulation or emulation. Why it matters? It's not only a semantic issue, because now or in the near future, each time you want to mimic a model, be for the sake of aesthetics, for analogies, for knowledge, for beating classical computers, it is very important to say, what do I need? What I need to prove and what I choose. You see, so I find it relevant that the next time you do a quantum simulation in theory or an experiment, you ask yourself what exactly you are doing. The physics may be different. I would say that for the very pragmatic people that just want to build classical computers, it doesn't matter at all if you are mimicking the internal structure and it is a simulation. What matters is that the output gives you the new physics that you wanted to get. So even though you see, open the box and there is nothing like the system you wanted to simulate, but if the output tells you what you wanted, then that's fine. Okay? So that's an interesting issue. Next time I will be able to answer if somebody from the general public asks me this difference. We don't make. In fact, the computer scientists have even more details. They have a term called virtualization and so on. So they are really. It's good to study what these guys are doing to know exactly what is our stuff in quantum simulations. Okay. So now a little of publicity for more technical things. In our group in Bilbao, as I said, we have been developing these general quantum simulations of relativistic quantum systems for different purposes. The main one is just for fun and to prove that relativistic quantum physics can be encoded in non-relativistic one in an efficient manner. But also we have been boosting strongly applications, you see, and beating classical computers. And then given, I have to thank many people for all the things I'm saying. Don't blame them, blame me for the opinions that you don't like. But the last one was with Jake Taylor in the coffee break. We're discussing topics. But I was much influenced by Rainer also. Some years ago, Rainer, who is a very enthusiastic researcher and sometimes pushy, told me, no, let us make an agenda. And the agenda was first the Dirac equation. Of course, the Schrödinger was there. Then free particle, Zitterbewegung, free particle with a potential Klein paradox, quantization of fields, quantum field theories, and so on and so on. So we really made an agenda on how to interrupt ions to develop quantum simulations that can really reach higher level. And Rainer was very insistent in the story of fermions, and there is a rule in our group in Bilbao that each time we hear a big shot saying that's impossible, we do it, and we reply with a PRL, because this is a good drive. No? Say some people are wrong. So we were very disappointed that everybody said, no, only optical lattices can simulate fermions. See, and we said, yeah, but let us try to do it in ions. It's impossible. You have to use Jordan-Wigner transformation, and with this, you have only efficiency for one dimension, but not for two. And you can have a look to these papers where, thanks to the work of many people here, we realized that if you combine the Jordan-Wigner transformation that maps spins into fermions with the Trotter methods, no, the digital quantum simulations that was mentioned in the talk before, and the multi-qubit Mermer-Sorensen gates, you can build a packet that is able to make quantum simulations of interacting fermions in trapped ions in an efficient manner. So Lucas will give a talk next week. Most of you will not be there, but I just mentioned, profit that he's there, and you can have a look to these papers where we show how to simulate quantum field theories in trapped ions that involves fermions, interacting fermions, a Holstein model, and so on. You see? So probably these experiments cannot be done now, but we wanted just to say that a little perhaps ahead of our experimental time now, but it will be possible to implement fermionic models in an efficient manner in trapped ions. See? So there is a future to spin models, which is mostly what is being done now. So you should be happy, at least, that it's not a big crunch coming, or that the optical lattices will dominate the universe. You see? This is more or less the announcement of Lucas' talk. He will describe most of the work with details, as many details as you need, and it will be next Tuesday, I think, right, Lucas? So I copy this slide. So now a second publicity, but here I will give you more details. We have created very recently a new concept that we call embedding quantum simulators, and in this I would really be happy that you can get some of the concepts, because I find it extremely relevant. Again, a little bit ahead of the experimental time for the applications, but you will see that it's very interesting. So with Jorge in 2011. We always read what we shouldn't. I was reading this nice comment of Frank Wilczek in Nature Physics about Majorana returns, and I was reading the biography of Ettore Majorana. He disappeared in the fair. I mean, it's a lot of fantasy about it because of the Majorana fermion too, which is boring to me. But anyway, and we produced this nice paper in PRX where we said, is it possible to make quantum simulation, not of a physical model, but some operations that are forbidden by nature? See? Don't ask me why. It was just really a nice drive, hard work. And then we discovered how to make a quantum simulation of, for example, an operation that is called complex conjugation. I don't know if you are familiar with this, but if Dave Wineland brings you a trapped ion and gives to Peter and said, look, a trapped ion, pure state, wave function. See? But you don't know what is a wave function. And then your challenge is to apply the complex conjugation to this wave function. The answer is that it is impossible. No? This operation, applying a complex conjugation to an unknown wave function, you can compare it with the no-cloning theorem. It's just impossible. It's not unitary, and it is not inside quantum mechanics. Okay? Then we said, can we mimic things or operations that are forbidden by nature? And then the answer is yes. No? And then we discovered a set of things, 3 discrete symmetries, complex conjugation, charge conjugation, time reversal, are possible to be mimicked in the lab. Okay? Don't ask me what for, just enjoy. Yeah? Don't forget your grants, just enjoy. Any physicist enjoys. Say, wow, can I mimic? See? And why it is relevant to mimic that? Because every day in the paper and in MATLAB, in the classical computers, we do this kind of things. Right? When you want to calculate a correlation or the, let's say, the square of the wave function, or when you want to calculate, for example, concurrence for pure states, you use complex conjugations and you calculate them. And our question was, if you are constantly using this in the paper and in classical computers, can a quantum device can mimic and reproduce this physics? And the answer is yes. And this, you can have a look in this paper. I will say more things about this later. Then we continued the game because we found that it is a nice game. And then we said, this is a PRL of very recent, of end of August 2013. Now we show how to break a little bit quantum physics in the simulation. Can we also break special relativity? And the answer is also yes. And then you can have a look to this paper where we prove how to make the quantum simulation of non-causal physics. See, so that was the game. We break quantum mechanics, we break special relativity, and then we said, now let us make something useful to get some money. Sometimes it works, sometimes not. And then we realized that the general concept of embedding quantum simulators appeared, and I will give you more details about this. So we proved that there are ways of making not a first order simulation, but a second order simulation. So we make a quantum simulation and we use again another encoding so that we can compute correlations, propagators, concurrence, entanglement monotones that are requiring full tomography in a more efficient manner, as I will tell you now. Okay? So what is the story of embedding quantum simulator? As I said, Jorge will talk about this next week, but I will advance some of the results because I find this very important. Formally, you have here a simulated space. Take your spin model, your fermions, whatever you want, you see, and then you say, I have a unitary operation and a wave function, but now I will encode this in a simulating space where assume that it's just a Hilbert space that is a little bit enlarged. So this Hilbert space is larger than the simulated space. And then you say, I want to apply in this simulated space, for example, in a spin model, I want to apply a complex conjugation or do something like that. That is just impossible. See here, K is complex conjugation and apply to a wave function, but you cannot do this. See, Tobias, Reiner, nobody can do in the lab a complex conjugation of a wave function. But if you encode these dynamics on in an enlarged space that essentially has a Hilbert space of dimension multiplied by 2 compared to the previous one, we challenge ourselves of building an embedding quantum simulator such that the complex conjugation is a physical operation, so that you have accessible this for whatever you need. See? And that's more or less the game of the story. We use it in the original paper in 2011 for building the wave equation of what is called the Majorana equation and to turn it real in a certain physical space. This is really a pure curiosity. I don't want to insist. This was just for fun. But look, this wave equation, you see, is very similar to the Dirac equation, only that the wave function here appears as psi and in the other side as complex conjugate. You can find this in the literature. It describes some grand unified models beyond the standard model. Doesn't matter. But we said, is it possible to take this wave equation that is beyond quantum mechanics, because you cannot factorize a Hamiltonian. You cannot factorize because you have psi here, you see, and to encode it in a physical one so that you can simulate it? And the answer is yes, and it is with this concept of embedding quantum simulators, making a second encoding such that complex conjugation is allowed. When we did that, for the people that love fundamentals of quantum mechanics, I mean, we don't have time to work in everything, but we discovered that when you build this pseudo quantum mechanics, if you want, something very funny happens. What we call now the Majorana wave vector has a property that the global phase is unobservable. That's very funny. Don't ask me details now. I can explain you later because if not, I don't finish my talk. But you see, it's enough that you change psi by psi complex conjugate, and this pseudo quantum mechanics has the global phase as a dynamical observable. It's really, really crazy. And it contradicts one of the axioms of quantum mechanics, the following, that a physical quantum state is not described by a ray in the Hilbert space, but is described by a normalized vector. See, so we had to make this research. So we can fake quantum mechanics that does not exist with these techniques. You see? Now let me tell you briefly how you encode. For the sake of the complex conjugation, is very simple. If you take just a qubit with two complex numbers, the encoding that you have to do to allow for complex conjugation to become a physical operation is just to separate in real and imaginary part and to encode it in a four-dimensional wave function like this. I mean, I don't want to take the details of Jorge because Jorge will explain it next week. But formally, this is, of course, a non-physical operation. There is nothing in nature that can separate a complex number in real and imaginary part. But this is just for the initial state. You see? And once you do this, you can transform the Hamiltonian, you can transform the operations, you can transform the physical observables, and you are able to build a dynamics, as you see here down, you see, that this unphysical wave dynamics is transformed into a physical one. That's more or less the game. At this point, you can continue the theory for observables. We gave here an example of helicity if you want, and this is a picture that you can keep in mind, which is a summary of this PRX, which says just that complex conjugation, charge conjugation, and time reversal can be made physical into a quantum simulator if you are able to make this embedding. Okay? The story of the breaking special relativity, I will say nothing. I just this Jorge will tell you later. But we prove also. I don't know how familiar you are, but you say, why do I want to break special relativity? The answer is, is related to some ignorance, perhaps, in our practices. But I don't know if you know that a Lorentz transformation, that is just a mathematical transformation that helps you to describe physics in one reference frame into another one, is not always a unitary operation. You know? So it's not always a unitary operation. So if Reiner makes an experiment and he wants to describe his physics in the lab in another reference frame making a Lorentz transformation, in general, this cannot be done physical. You can only do it on the paper. And with these techniques, you are able to make parity operators in space and time and Lorentz transformations. The last part of what I wanted to say is in these embedding quantum simulators is something that you will see the value. No? Formally, we realized that if somebody is making a quantum simulation, for example, of 10 spins, you have 10 spins, 10 trapped ions, and you are making a sophisticated quantum simulation where it will be very hard to reproduce classical. And at any moment of the evolution, you need to know, for example, what is the bipartite concurrence or an entanglement monotone associated to this multipartite system. So you see, I am beating classical computers. I am putting 10, 20, 30 spins in a sophisticated model, and I am really doing some stuff. But if the question at the end is, calculate me a correlation, a propagator, or an entanglement monotone, you will not be able to do, you see? Because formally, there are some correlations that are physical, are not observables, but are physical, that require full state tomography to be calculated. One of them is one of these entanglement monotones. See? If you have simulated a beautiful model with 30 spins and you need to calculate one of those correlations, you would need full tomography. This means a Hilbert space of 2 to the 30 times 2 to the 30, and it will be just impossible. See? With this kind of embeddings, that Jorge will give details next week, you are able to make this quantum simulator in this embedded Hilbert space such that at any time that you want, you can measure concurrence or some correlations or propagators with very few observables without having to make full tomography. You see? So from that point of view, this concept of embedding quantum simulators has the following recipe. Each time you want to make a quantum simulator, tell me which kind of quantities, observables, or just entanglement monotones or correlations you will want to measure at the end, and we will fabricate an embedding such that these quantities are coming in an efficient manner. You see, so in this example we just gave this example of these correlations, and in general you will need full tomography, and in the enlarged space they are just banal unitary operations that can produce these quantities. Right? So how many minutes I have to finish? Okay, so I stop here. I don't want to bother you much, but summarizing, just to summarize everything I said, I think there is much more than just trying to please the beating classical computers in quantum simulations, and by just playing the game of making analogies, having fun combining relativistic things with non-relativistic, or creating physical operations, you can reach to very useful things that, as I said, it's not your problem now in the lab, but when you will be able to have really massive quantum simulators with many particles, you will end up by asking questions about correlations and entanglement monotones that will require full state tomography. And if you don't use something like this, like embedding quantum simulators, you will be wasting your time, because full tomography of 20, 30 qubits, for example, is just impossible. Okay, thanks.
Okay, thanks. So, are there any questions? Yeah.
So, Enrique, I'm kind of intrigued by this embedding story. And what I missed in the discussion was a sort of simple cartoon about how you go about trying these ideas out. And could you maybe just provide, for core theorists like me a simple picture where I can understand this for a single spin, and I want to do something like this complex conjugation. I didn't really
for the complex conjugation.
Sure.
Yeah. So essentially, I think this is the best. Okay. You can see it here. Yeah. So essentially, a qubit. See, real part, imaginary part. It's very, very simple. If you just take this information and you encode it like this, real part and imaginary part, and I tell you, complex conjugation, change this qubit into this state. So trivial operation. If you check here, the complex conjugation will just turn the four-dimensional vector in this way. And if you see, while this k, a complex conjugation, is a forbidden operation, in this enlarged space, it is just sigma z times identity. You see? This is very basic at that level. The relevance comes when you have a complex system and you need a correlation that involves a complex conjugation for 10, 20, 30 qubits. Because then, essentially, you are running your simulation, you stop. The only possibility that you have with 30 qubits, for example, to calculate a complex conjugation is to make full tomography, put in a classical computer. In the classical computer, you can apply complex conjugation, you encode it back, and then you continue. But with this concept of this embedding, what you do is, instead of simulating, as we call it, a one-to-one quantum simulator, you make it in the enlarged space, and then at any time you need a complex conjugation, you just apply a sigma z times identity, for example, and then you continue. And the complex conjugation was automatically encoded in the simulation. That's more or less the general picture for one qubit. But anyway, we discuss later.
Right. I think I can understand this now.
Right.
But it sounds like it's really about taking a bigger group and artificially producing a subgroup, which is the one that was the physical one to start.
I fully agree. Because you see, some people, when I have mentioned this, they think, again, like with the Dirac equation, that we are making real and physical operations. We cannot. We cannot.
Okay, so we'll talk technical details.
Yeah. So just to end with a clean sentence, it's not this. Everything that is done in quantum simulations nowadays is what we call one-to-one quantum simulators. Each time you want something more, you need an embedding such that these operations are allowed. So it's not. It's a combination of a quantum simulator with a quantum algorithm encoded to get this additional information. Yep.
Okay. Just one question to understand this again. I'm sorry. You're simulating space on the right hand side. This is now really also the embedding of the true Dirac equation, the scheme of in a sense. So in the Dirac equation of base charge symmetry.
Yeah.
So it's because the charge symmetry just exchanges n in particle. So and this is the reason why in the Majorana equation where you have a mass breaking charge.
Yep.
Okay, so it's just
a
equation.
Okay, if there are no more urgent questions, let's thank Enrique again. Very nice talk.